bit more about the scheduling. One of the things, the way the Cray compiler works when it compiles OpenACC is the Cray compiler has its optimizer in it, and if it also has something that generates PTX, and PTX is like assembly code for GPUs. It's not quite the very lowest level, but it's the lowest level that you'll ever see if you're not working for an NVIDIA. So the compiler generates this PTX directly, in the same way that NVIDIA, the NVCC compiler, takes CUDA and generates PTX. So CUDA and OpenACC run on the GPU in a very similar fashion. And this is why the interoperability works well. But what the Cray compiler doesn't do, some people say, oh, could I see an intermediate CUDA that's where the Cray compiler, the compiler generates a CUDA and the CUDA is then compiled to the PTX? And the answer is no, because it doesn't exist. The PGI compiler does have an intermediate CUDA, but it's unreadable. Where you can read it, but there's no loops. There's just, jump non-zero type statements. It's very low level and not that useful. So the reason Cray doesn't do an intermediate CUDA, other than it would impact performance, is that that would be a source-to-source translation, and it's very hard to preserve debugging symbols when you do that. So when you use the debugger, you're taking advantage of the fact that it's going straight from your Fortran or C to PTX with the right dwarf information, that the debugger knows the right variable names. And so the decision was taken that using tools like a debugger is far more useful to users than having an intermediate CUDA to look at. So in this talk, I'm going to go through a few directives that I haven't talked about before, a little bit about the difference between parallel and kernels, and a little bit of lessons I've learned along the way when I've been using it. Minimizing data movements is something that you want to do, and we had this idea of data regions. So you should keep the data on the GPU as long as possible with big data regions that span as much of your code as you can. Only move data when you need to. So within that data region, if you need to move some data back to the CPU, you don't want to synchronize everything by ending the data region. You can use a directive called update to just move the amount of data that you want to move. And when you move the data, only move what you need. If you don't need the whole array, don't move the whole array. If all you're trying to do is move the edges of the array, the halo, because you're going to do MPI to send them to the nearest neighbor processes, don't move the whole array, just move the halos of that array. And again, this update clause allows you to do that. So with a data region, there's synchronization points at the start and the end automatically, because you've said copy in or you've said copy out. But within it, there's no synchronization. And the way you add this synchronization is you use the update directive. So, and this is a manual copy. This isn't something the compiler does automatically for you. It's you saying, I need to get these values back to the CPU now, or I need to send updated values to the GPU now. And these are directives, and the directives are whatever, hash pragma ACC, and then update host A, B. And what this will mean is that the arrays A and B, which are on the device, the GPU, these will be copied to the host, which is the CPU. So host is telling you where they're ending up there. And if you do want to copy them from CPU to GPU, you say update device A, B. It could be, it's just a comma-separated list of arrays. In OpenACC 2, instead of using the word host, you can use the word self. This is supposed to make things clearer when you have self-hosted accelerators. But when you start to think, what does a self-hosted accelerator mean? I don't think it makes anything more clear, but you'll sometimes see self instead of host for this keyword. So you put these directives in the code yourself at the point where you want this data to move. And by default, it's a synchronous operation. The CPU will wait while that data is moved. Now, you may want to get the data moving and do something else whilst it's moving, and we'll cover later on how you do that. But if you don't tell it to do it in the background, it waits for this operation to complete. If you only want to move part of an array, then you want to use a syntax, an array section syntax, a slicing syntax to only move some of the data. If you use Fortran, well, it's just the same as you'd do. You'd say to send the first n elements of the array, you'd say update, and then you'd say a brackets 1 colon n. And that would be element 1 to element n. If you're using C or C++, it looks the same, but it's different. So here, this doesn't transfer elements 0 to elements n. That would be n plus 1 elements. It transfers n elements starting at 0. If you use one language or the other, it's easy, you just remember. If you're trying to do examples in both of them, you end up making mistakes because you forget. The runtime commentary, that Cray-ACC debug, is brilliant for finding these errors because it tells you the name of the array and it tells you how many bytes. So you look at the number of bytes, you divide by 4 to tell you the number of floats, and you immediately see, I've done one too few. That's why I'm getting the wrong answer, because the last array element didn't move because I mixed up these syntaxes. If you do slices on multi-dimensional arrays, it has to be a contiguous block of data. What that means is that if you're doing Fortran, you have to have all of the elements in the left ones, and then an incomplete slice has to be on the right. And you can only have one incomplete slice. And then that's one block of memory. For C, it's the same, except it's the other way around. So for C, the fastest moving indices, which are on the right, have to be complete slices, and then the incomplete one is only one of them at the left-hand side, because it has to be one block of memory. If you need to send a number of slices, you'll need to have a number of separate directives. If you're doing C especially, you'll often see, you'll do some OpenACC and you'll see errors from the compiler, unshaped pointer, which is a really useful error message because it tells you nothing. What it's telling you is that I didn't know how much data to move. And that's because in C and C++, arrays are just pointers, generally. They point to the start of the block of memory. So if you say, copy C, where C is an array, what you're really saying is, C is a memory address. How much data should it move? It doesn't know. So in C and C++, if you're using dynamically allocated arrays or arrays passed by reference, you will often need to specify the data movements explicitly, and you will need to specify the slice, even if it's the whole array, just because the compiler's got no other way of knowing how much data you plan to move. In Fortran, it's different, because in Fortran, an array is not just a pointer. It's actually this array descriptor, which contains all sorts of information about the shape of the array and the size of the array. And so the compiler can hook into that information to work this out for itself. But in C, you often have to be explicit. So if you hit these errors, that's what you need to do. No, n can be known at runtime. It's fine for n to be a runtime thing here. It's in the pragma and it's compiled, but all of these things get turned into API calls, calls to runtime libraries. And these can be passed arguments. So this n doesn't have to be fixed at compile time. It can be determined at runtime, which if you're using dynamically allocated arrays, of course, is what you want. Yeah, that's fine. No, you give the units in array elements, and yes, it knows that it works out what type it is to get that right. Yeah, so you work in elements, not in bytes. So sometimes you need to put more data clauses in than you thought you'd have to, and if this was a present clause, you might have to say present C and a shaping argument there. This is what we've been talking about before. This was to do with present, that if you want to share data between kernels, then instead of saying copy, copy in, copy out, create, you just use present. And then it has to be there on the GPU. And it will use the version that's on the GPU. And it will check whether it's there. If it's not there, you get a runtime error. And it does this because the compiler and the runtime maintain a table that know which CPU memory addresses have been mapped onto the GPU and where they are in the GPU memory. And so it checks this table to see whether it exists there or not. If you sometimes call a routine from inside a data region and the data is present, but at other times in the same code, you call the same routine from outside a data region and you want the data to be processed on the GPU, but it's not on the GPU, so it should first move there. What you say is, instead of using the present clause for these kernels, or this in the data region, you say present or copy in, present or copy out, present or create. And this will it'll first check, is it present? If not, it will follow it'll either do copy or copy in or copy out or create, just like we were doing before. So the data will always be processed on the GPU. It's just whether or not it needed to be moved to the GPU first in order to do that processing. As I say, for a lot of real codes, where you know that the call tree is such that all calls to this routine are within this data region, and you know the data must therefore always be present unless something disastrous has happened, it's better to use present because you get a runtime error rather than get just a wrong answer when your code runs to completion. The other thing you might say is that I'm going to call a routine. Sometimes I'm going to call it from a data region, from inside a data region. Sometimes I'm going to call a routine from inside a data region. Then the data is this is a bit confusing. I'll change this around. Sometimes I'm going to call this routine, and the data is on the host, and I'd like to process the data on the host. Sometimes I'm going to call it, and the data is present on the GPU, and I want to process it on the GPU. How do I decide what to do there? Well, there's an if clause. An if clause can be applied to the parallel kernels. I think the data as well, data regions. And you can decide at runtime whether to execute your loop nest on the CPU or on the accelerator. It executes on the GPU if it's true, otherwise on the CPU. So that's good, but the argument here is what goes inside that if clause. If what? I mean, one way we could do it is we pass a logical in. So we pass in data that we know is on the CPU, and we pass in a logical variable that says true, well, sorry, false. And we know, or we pass in data that we know is on the GPU, and we pass in a logical that's true, and then we just put that logical in the if clause. Would be one way to do it, but we'd have to put this extra logical in there, and you're changing your code to do this. There is a runtime library call that you can do to check whether data is on the CPU or the GPU. So you could use that runtime call if this is really something that you'd want to do. It's not something you use very much. Library developers use this more, but there is a way to do it. We'll see later on how to do that. But this is where you're wanting to process the data locally. If the data's on the CPU, process it on the CPU. If it's on the GPU, process it on the GPU. And that's probably more like what you want to do than the present or copy, where it's always going to be on the GPU, but it may end up moving there. If you look in that book, you'll see there's two directives in there, parallel and kernels. And if you read the description of them, it's really confusing because it sounds like they both do the same thing. They both seem to take a loop nest and turn it into a kernel on the GPU. So the two questions you probably ask yourself is, why are there two of them? And the other, why are they different? The parallel region is more prescriptive. It's much more like an OpenMP programming model. It means put this on the GPU, parallelize it, even if it leads to incorrect results. The kernels is more an invitation to the compiler. Could you consider parallelizing this? But the compiler may refuse to do it because it says this loop nest isn't parallelizable. If you really want to know all of the differences, there's an article on the PGI website that describes these. Why are there two of them? Because when OpenACC was formed as a standard, it merged together two existing things, which was the OpenMP work so far, which the Cray compiler was kind of supporting, and the PGI accelerator programming model, which PGI were developing. And parallel is kind of what was coming from OpenMP, and kernels is kind of what was coming from PGI. And in the nature of all collaborative efforts, they both ended up in the standard. So that's why there's two. They just have a different heritage. Which should you use? It's up to you. I mean, I come from a more OpenMP background. I quite like the, it'll definitely do it, but I might get a wrong answer if I tell it to parallelize something that isn't parallelizable. It's up to you. Both of them, both parallel and kernels are supported by all the compilers. There shouldn't be a significant performance difference between them. There is sometimes, but there shouldn't be. So everything I talk about is parallel. Parallel loop is really two directives put together as a shorthand. You can use them separately if you want to. The data clauses go on the parallel directive. Why would you want to do them separately? Tuning is probably the main reason. Otherwise, I wouldn't do it. I wouldn't split them up, because you could do this. You can put loop above each one of these, but you don't need to do that. Inside a parallel region, what happens? When you launch it, it starts all the threads up. And all the threads start doing the same thing together. So they execute redundantly. Everything is doing the same thing. You only get work shared between the threads, rather than all the threads doing the same thing, when you get partitioning. And you only get partitioning when you hit a loop. So if you just put a parallel directive, what happens is you can either put it around scalar code, and this would just be scalar code that executes on the GPU as scalar code. If you put a parallel region around a loop nest, but didn't put any loop directive, every thread would do every iteration of the loop nest, which is probably not what you want. It's only when you put the loop directive in that you spread the work out. You have this partitioned mode of execution. So if you start splitting the parallel and loop directive, you open yourselves up to all sorts of problems, such as forgetting to partition the work, so you do everything does everything, but also you end up with race conditions. So you might say, well, what do I do here? Well, it seems a bit silly to initialize these reduction variables on the CPU and then copy this 0 value to the GPU. Why don't I initialize it on the GPU? So I'll put the initialization statements inside a parallel region. So this will execute on the GPU, and I'll save copying 8 bytes of data here. And that sounds like a good idea. The reason that's not a good idea is because there's no barriers on the GPU in CUDA or OpenACC. There's no barrier here. There's no barrier here. The barrier only comes here. So all the threads will set this to be 0, but then some threads will be quick at that, and some threads will be slow, and other threads will already have started this and be overwriting values, and the slow ones will then destroy half of these values that you'd added into T. There's race conditions everywhere. There's plenty of race conditions in OpenACC. You have to be careful, and this sort of thing, you think this is a little optimization, but actually it's a big problem. So don't try and do this because you think, oh, these code blocks could overlap on the GPU, or I could save copying a bit of data. If you want to do this, the async clause is a better way to do it. Big parallel regions, which is what you do in OpenMP, are not a good idea on the GPU because of the lack of barriers, the lack of synchronization. OpenMP has, when you end a loop, it's a wait, unless you say otherwise. When you end a parallel region or end a loop inside a parallel region, there's no implicit barrier until you end the parallel region. So it's like end loop is like end do no wait in OpenMP if you've done that. So my advice is don't do this. There are better ways to do it. So here, what's gone wrong here? Every thread does every loop iteration because we forgot a loop directive. Here, it's the same thing. There's a race condition because there's no barrier after this is set. Here, we had a good idea that, well, why don't we get overlap of these kernels on the GPU by using 2 loop directives inside one parallel region? There's a race condition between here. Yeah? Yes? It will use by default 128 threads per block. Yes, it's a default decision. The number of blocks will be related to n, except here it's not partitioning. Every thread is going to do, I don't know how many thread blocks you get, I don't know, but either way, it's just not what you wanted to happen usually. Every time you put a loop directive in, you must repeat the reduction clause. It's really easy to forget this and you get the wrong answer. Here is fine. I've just said parallel loop reduction for the whole loop nest. That's fine. Here, for some reason, I've put this loop directive in there. Maybe I thought I wanted to put a loop directive. Maybe I put it in because actually it's got a tuning clause that I've not shown you yet. Either way, this code will be wrong because there is a reduction on T in here, and I forgot to say reduction. I don't need to say reduction here because it's only if I put a loop directive in myself, I must repeat the reduction clause. Here again, I forgot it here. This was all right because I've put a reduction on every loop directive. I just didn't say parallel loop. I've separated them there. So that would be all right, and that would be all right. These are wrong. It's very easy to forget this. The code actually probably runs faster here, but that's because it's doing the wrong thing, and you get the wrong answer. Running OpenACC and OpenMP together, I'm not going to talk about that now because it's a more advanced topic. I can discuss it with people if they think this is something that they'd like to do. So I was going to go straight on to Are there any questions on that? I mean, that talk's a little bit of a mixed bag. There's kind of little bits of this and bits of that all put together because they didn't really fit anywhere else. The update, I mean, they're things you do use. It's just they're kind of odds and ends. So what I want to talk about here is a bit of performance tuning. So I'm assuming now that you've been through the exercise of putting your data regions in, nested data regions where you need them, but you've sorted out, you've minimized the data movements. You've done that, and now you think, well, you know, my runtime is dominated by my compute kernels. Can I improve the performance of the compute kernels? How do I go about doing that? And so I'm going to talk a little bit about kernel scheduling, understanding how loop iterations are divided between threads, and then how you can make changes to that are hopefully improvements. So this GPU kernel is executed by a large pool of threads. So these threads are like little computational things on the GPU. They're not physical things. They're not physical cores, but they're things that run on the cores. So you've logically divided up the work into these threads. So the loop iterations are divided over threads. The threads are divided up into these thread blocks, and each thread block gets given to this vector processor on the GPU. And within the thread block, you've got these warps. The fact that 32 of the of these floating point units on the GPU share a single instruction stream. So they have to do the same thing at the same time, but just operating on their own bit of data. CUDA doesn't make the warps explicit, but you do need to know about them to understand the code performance. OpenACC, the scheduling is very similar to CUDA. There are some differences. Gang is the same as thread block. Gang, so this is where you've got a set of threads. They're going to go off to run on their own little vector processor with its own little cache of memory and with its own vector instruction stream. But how these thread blocks execute, you've got no control. They don't execute in sequence. You've got no control over this, and there's no barrier between them. Vector is the threads within a warp. So that's 32 threads that are doing the same thing at the same time. The intermediate one is that if you have in CUDA, let's say, 64 threads in your thread block, the warp length, which is a hardware thing, it's the length of the vector instruction, is 32. So when you say in the thread block, 64 threads are going to be doing the same thing at the same time, actually they're not. They're going to do it as a block of 32 with one vector instruction and a block of 32 with the next vector instruction. So it's divided up into groups of 32. This is like in the CPU if you're using SSE instructions of length 2 or 4 or whatever, that if you've got an array that's size 8, it will do that as 4 SSE instructions of length 2. It's vectorizing it. It's just the vector length isn't quite the same as the vectorization length of the kernel. And it's the same thing here. So when you have the threads in your thread block of 64, you've got 2 vectors are needed to do each bit of work, because you've got 64 threads. These will execute as 2 vector instructions. So vector is the threads within a warp. It's 32 threads doing the same thing at the same time. Worker means in order to do 64 threads per thread block, I needed 2 workers, each of length 32. So OpenACC kind of makes this warp more explicit, because instead of having just thread block and threads per block, it splits threads per block into vector, which is the actual length of the vector instruction, and then how many of these will do the work associated with a thread block, which is the worker level. This is, if you're new to this, this is a bit complicated. But this is a performance tuning. This is why I didn't talk about this morning, because this is the only thing, this is when you come to tuning your kernels, because you've done all the data region optimizations, you might think about this. So when a loop nest is divided up by the compiler, the loop iterations are divided up into gangs of workers. The gangs execute on these vector SMs. The workers are divided up into sets of vector instructions of width 32. And these are called the warps, or the worker in the language of OpenACC. There are many different ways to take a group of loop iterations and divide them up in this way. And how this division is done will affect the performance. The compiler makes a default decision. The tuning comes in where you go in and you say, actually, a better division of this work would be this. OpenACC, more than one loop in the loop nest is divided up. In OpenMP, only the outer loop. So vectorisation is the first thing. Make sure all the kernels vectorize. That means that the compiler is efficiently turning what you're doing in your loops into vector instructions, the minimum number of vector instructions to do all the work. If it's not, it will take more clock cycles because it will be using more vector instructions, but in an inefficient manner. How do you know if there's a problem with this? Well, first of all, you've accelerated all your kernels. So with this Himeno example, there were 4 kernels. We accelerate them. We look at the profile after we've accelerated it all. And we discover that that little copy array that said P equals work 2, which we know from the CPU should take very little time, suddenly that's taking far more time than the stencil. That can't be right. There isn't much work there. It's a signal that something's gone wrong. So when a kernel is slower than you might expect, there may be a reason for it, but it could be that there's just a simple vectorization problem. Look at the compiler commentary. You should see 2 little g's down the side. If you don't see 2 little g's, it hasn't divided work across threads within a thread block and between thread blocks. So in that example, we saw 1G here, 1G here, and there were messages for the 2 levels of parallelism. In some cases, you might see 3 little g's because it's using the worker level as well. But if you only see 1 little g and you haven't got a single depth loop nest, you've got a problem. If you've got a single depth loop nest, you'll see 1 little g, and these 2 messages should sort of be all together, that it's partitioning it over both levels. If it's not using both levels, you've got a problem. So you should see that you've got 1 loop that says it's partitioned across threads within a thread block. Which loop should this be? Generally, it should be the innermost loop, because the innermost loop on the CPU is usually the fastest moving array index, because that gives best cache usage. And the same will be true on the GPU. If this inner loop is not vectorized, it's not divided over threads within the thread block, why not? Is it because your algorithm isn't vectorizable? Can the loop iterations be computed in any order? If not, you may need to rewrite the code. It'll probably work much better on the CPU as well. So if you're packing a buffer and it just uses this incremented index to work out where in the buffer to put the elements, and then at the end, it uses the last value of this to tell it the size of the buffer. And you see this in an MPI code. It's quick and dirty code to write. That doesn't vectorize because it needs to know it can't compute these loop iterations in any order and get the same answers. It's much better to use a computed loop index and a computed size, and that's vectorizable. There's lots of literature on vectorizable algorithms, but it may need something that's changed in the code. If the loop iterations can be computed in any order, then maybe the compiler is just being stupid. They are from time to time, as you probably know from experience. So then what do you do? Well, then you go in and you help it. So one thing you can do is you add a directive above the loop, the inner loop that should be vectorized, should be spread over threads within the thread block, and you give it a gentle hint. You say, you know, these loop iterations are independent, and then maybe it'll say, oh yes, and then it does it for you. So you check the compiler feedback. If it still says, no, I'm not doing it, then you just go in and you give it a direct order, and you say, this loop should be divided over the vector level of parallelism. And then it should do it. Then you should check the code is still correct. Perhaps the compiler wasn't being foolish and it had spotted something that you didn't, and there was a dependency. So only put these in, when you need them. And remember, repeat any reduction clauses when you add these tuning directives, if you need them. Sometimes the inner loop is vectorizing, but performance is still bad. Well, why might that be? It might be that actually the inner loop is the wrong loop to vectorize. If the inner loop had a very low trip count, a trip count of 5 or 6, the vector instructions are width 32. Yes, it can do a loop of length 6 as a vector, but it wastes 26 lanes of the vector instruction. So the performance is bad. GPUs are a very poor serial processor. You want to use the full vector width. How would you know? You might know that this trip count here is small, or you might use Cray to tell you it. We'll talk a little bit about that later. If that's the case, then you say, actually don't vectorize this loop. So then you can say, do this loop sequentially. Then every thread will do every loop iteration here, and instead it should divide up this outer loop. You may get better performance as well, because then, if this is a divided loop, a partitioned loop, t is a reduction variable. If it's a sequential loop, every thread sets t to be 0, adds up its values of t, and gets the answer. this isn't a reduction variable, it's just a private variable if the parallelism is all at this level. So it can give you better performance like that because we've avoided a reduction variable that we would have had for t. When you do this, you should now see that you've said this loop must be sequential, so now it should go up and it should vectorize the outer loop. If it doesn't, well, then you'd need to put ACC parallel loop vector there to be explicit and tell it to do that. So just to talk about this a little bit more, we forced it to vectorize the outer loop because this was a small loop. Well, now performance isn't going to be brilliant here because at this stage, the vector index is not the fastest moving array index. So when I look at threads 1, 2, 3, 4, 5, they're not loading a contiguous chunk of memory for their particular value of m. They're striding through memory. So I won't load this data in one vector load. I'll need 5 or 6 vector loads to get all of that data. And I'll be polluting my cache when I do that. Loads and stores from global memory are slow, so performance will suffer. So it made sense from a performance point of view to make this loop sequential, but that did change how efficiently I was loading data from memory. What can I do there? Well, one is live with it. That's the way your code is. You know, that's the way the science is. I don't get peak performance, but there you go. The other thing you could do is perhaps you could reorder that array. It would mean changing your code to transpose this array and make the I index the fastest moving, because now when 32 threads in a vector, in a warp, want to load memory, they're loading a contiguous chunk of memory. It would mean rearranging my data structures. In a small code, that's not much work. In a big code, it could be a lot of work. It might benefit you because you get better vectorization on the CPU. It might not. It's hard to know, is it worth making those changes or not? You'd maybe want to use a test case. If you did make the changes, well, now the code would look like this. So I did some experiments with this code for different values of n, and I ran it with just the default schedule, so it was vectorizing the inner loop that was too small. Then I said, okay, make the inner loop sequential, but the data is now the wrong way round in memory. And then I said, okay, let's transpose this array in my application, which is only a test case, and see what happens. So green is the baseline. Telling it to make this loop sequential gives you blue. You get a big performance gain, massive. If I can also rearrange my data, there is a performance gain on top of that, but it's not as great. So just sorting out the loop schedule was enough to give me a massive performance difference, blue to green. And it became because I knew from my knowledge of the application that this loop was small and the compiler couldn't know that. If it is vectorizing well, it's performing badly, what do you do then? Well, it's whacking moles. You know, you look at the profile, which sticks furthest up, and you hit it. You go and look at that kernel, and then you move to the next one and the next one. And like all optimizations, there's no rule to do. What should you do first of all? There's 2 easy tuning choices you can do early on. If you were doing CUDA programming, you would often vary the number of threads per block to see if the performance changed. You can do that with OpenACC by adding a clause called vector length and then a value. And for the Cray compiler, they have to be multiples of 2, so powers of 2. The default is 128, but it's worth varying it to see if it changes it. It has to be fixed at compile time. If you program in CUDA, as well as specifying the number of threads per block, you also have to specify the number of thread blocks, which usually is number of iterations divided by number of threads per thread block. But you have to do it. In OpenACC, it will do it for you and make a default choice. But you can use a clause to change that number if you want. And that's another performance tuning you can do without messing about with the actual source code other than the directives. You can change how loops are scheduled. We've seen using the sequential clause, and we've seen using vector to tell it which loop to vectorize. But you can also tell it this loop should be divided over thread blocks, this loop should be divided over workers, this loop should be divided over vectors. And then you can make use of, and you can take one loop and you can divide it over multiple levels of parallelism just by putting the clauses together. So, plenty of freedom. What's the best thing to do? Well, technically, within a loop nest, you can't keep putting these in. You can only mention each of these once. You don't have to mention them, but if you do, you can only do it once, because it doesn't make sense to do it more than once. You can't say vector for this loop and vector for that loop. If you have a race condition and your code doesn't take too long to run, if you run it on a GPU with one thread and one thread block, it's a way of finding out if it's a problem in the code or if it's a race condition. But execution will be very slow. I'm not really going to talk about the vector length bigger than 32. This is here because it kind of fits in, but if people are interested in exactly how things are scheduled, I could talk about that later. One of the restrictions in OpenACC is that when you do a loop schedule, it is limited by the loop bounds, in that this loop is divided over gangs, over thread blocks, and that loop is divided over threads within a thread block. If you've got a tall, skinny loop nest, so you've got one very big loop nest and one very small, it won't schedule very well because it will try to schedule this one over thread blocks and this threads within a thread block, so it's wasting vector instructions because it's not, I'm assuming here small is much less than 32, so that's not good. If you've got a short, fat loop nest, so the outer loop is quite small, but the inner loop is big, you get good vectorization, but you don't have many thread blocks, and you need lots of thread blocks to hide memory latency. In both cases, small times big is very big. So you've got enough parallel work, it's just not divided very well between the two loops. So if you want to divide this loop, these iterations better, what can you do? Well, there's two ways. One is the collapse clause, and one is the worker clause. If you've used OpenMP, collapse does the same thing. So in this example where we've got two loops, if I say above the outer loop, I say ACC loop collapse to gang worker vector. What that will do is it will collapse together, and it will essentially, it's not the same, but essentially what it does is it makes them one loop with a combined trip count, and then it divides those iterations over the levels of parallelism on the GPU. It's broken down that strict hierarchy of one loop and the other loop, and each loop gets partitioned separately. It pushes them together and partitions them more evenly, and you get better performance. The compiler often does this automatically. If you look in the .lst file, you'll sometimes see a capital C and a message about collapsing. There's no guarantee it's faster, so it's something that you try, and it will only work for perfectly nested loops. So it has to be do, 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 end, do, end, do, end, do. You can't have do, a bit of code, do, and then end do's at the end. It's got to be just all the do's together, all the end do's together. I'm speaking Fortran here, but in C it's got to be 4, 4, 4, and then close all the loops in one go.
So you might do it on its own?
Yeah, so I would have a look first before you step in and see what the compiler did. This is when you look at the compiler commentary. So if you've got a 3-level loop nest, like the Himeno code I inside J inside K, if the loops are perfectly nested, collapse 3 to collapse them all together is probably a good thing to do. And then you say schedule it over the whole GPU. Actually, you probably don't need to say that. There's only one composite loop left. It's bound to schedule it over the whole GPU. And if you've got small trip count loop nests, this is usually the best thing to do. And you can, if you want, you could collapse just the two inner loops. So you'd say parallel loop above the K loop. You'd say collapse to, and then you just divide the inner two loops over the vector level and the outer level over the gang. There's no particular answer as to what you would do. It depends on the trip counts of your loop. It depends on how much work is inside the kernel. You have to try these things, and I'll show some examples of this later. Sometimes collapse isn't the best thing to do, or you can't do it because the loops are not perfectly nested. Then, using the worker clause explicitly can help. So that's where you would say loop gang above the outer K loop, loop worker above the J loop, loop vector above the I loop. And that changes the scheduling. It doesn't change the total amount of work. It does change how the work is distributed between the threads. Workers is a bit... Worker and vector are not completely independent, because a worker, when you have a vector length of more than 32, that automatically splits up into workers. So if you want to put a worker clause in, you might want to specify how many workers, but then you can't specify vector length as in threads per thread block. The only thing that makes sense is to say vector length of 32, because you're then saying vector only refers to single vector instructions, and they have width 32. Again, slightly more technical, this. Which should you use? Difficult to say. You probably want to do a comparison. I'll show some examples. If you've got perfectly nested loops, collapse is often better. If you've got imperfectly nested loops, worker can benefit, because collapse doesn't work there. So those are changing the scheduling. What other things can you do to improve performance? If you've used CUDA, you're used to the idea of using shared memory, of a user-managed cache of fast memory to try and reuse data. So if I'm doing a stencil where I'm doing a finite difference, the values of B get reused. When I calculate 3 different A values, each one will use this particular array element. If every time I do this, I reload it from memory, that can be slow. So could I kind of store these values in a cache and then reuse them? Would that help? The cache directive is a way of saying it might help to reuse this data if you can. Unlike a lot of OpenACC, it doesn't tell the compiler to do it, it suggests it. The compiler may ignore what you say, for good reason or for bad. Because even if it does respect it, there's no guarantee the performance actually improves. So what would I do? So here, I'm adding up some array elements between I minus some parameter radius and I plus radius. So I've got a loop here. I'm adding up these elements with some weight factor. What I would say is, well, you know, for thread I is going to use this data, this range of data, and some of that will be relevant to the other threads. The neighboring threads are going to reuse some of that. So what you say is that inside all of the partitioned loops, you say, from the point of view of this thread, I'm going to use this data, which I think might be useful to some of my neighboring loop iterations. The compiler can then look at that and it can say, yes, I agree. And for this thread block, overall, they're going to use a bigger block of data which reflects the fact that this loop iteration is going to go from 0 to 5, this one's going to go from 1 to 6, this one's going to go from 2 to 7, blah, blah, and this one's going to go to n plus 3. So if I were to cache an amount of data from 0 or 1 to n plus 3, all of the threads in the thread block could share that. And a lot of it would get reused. So for this example here, you may decide, from the point of view of I and j, there could potentially be some reuse on this range. Now, when you use this cache directive, you need to know how many threads are in the thread block to know what block of data should go into the cache. So the compiler needs to know this, and in some cases it's not obvious. And if it's not obvious, you need to start blocking this loop nest. And again, if you're familiar with CPU cache blocking and things like this, it's the same procedure. If you're not familiar with this, it's kind of a bit alien, but this is a bit more of a performance tuning. So don't worry about it for the minute. The tile clause is a way of providing this blocking information to the compiler. It's new in OpenACC 2. It's, from our point of view, quite an advanced thing to be doing, because all of the other tunings have been done. It also allows the compiler, if it wants, to use multi-dimensional thread blocks. And again, if you come from a CUDA background, you'll have heard of these. If you don't, it's a bit of a, I'm not going to go into them now. I have not, this is how you would use the tile loop, the tile clause. It's not something I've found very useful yet, but it is quite new. But in the codes I've used, it's not something that I've used a lot. There's more detail there on exactly what it all means. So if you're doing multi-dimensional caching, tiling the loop nest can help. But let's gloss over that for the minute. Scheduling, after data movements, scheduling is your biggest optimization. Getting the vectorization right is probably the thing to spend your time on. Collapsing loops, worker clauses can help, but I would get the vectorization right first. Caching and tiling are useful at the end. I will give some examples in a sec of exactly where they might be useful. Are there any questions on that?
One quick one. The execution of the threads are not ordered, right? There is no order. Thread number 1, thread number 2. So the caching cannot be effective. There's no order.
Well, what happens, I mean, if you've done CUDA programming, is that you know that, let's imagine there's 5 threads in your thread block, and they're going to reuse data. What you first need to do in your kernel is you first need to say, okay, the data that will be reused is this data. So the first job is to pull all of that data into the cache, because it's a user-managed cache, the shared memory. And then you synchronize within a thread block, because you can synchronize within a thread block to say, I've loaded all that data. And then you actually do the computation that's going to use that data. It's quite complicated to write it in CUDA, especially with multi-dimensional arrays. It's between thread blocks. There's no caching between thread blocks. So caching only works within one thread block that's on one vector processor, one SM. Well, this is why it can actually slow you down. It'll only be quicker if the data reuse that you're getting, the saving on memory bandwidth, offsets the cost of that synchronization to say I've loaded it all. Cache is not wonderful in the sense that you should always use it and it will always improve performance. There are examples, it's very easy to slow your code down using the cache. So use it as a performance tuning, but don't rely on it. And again, what sort of performance gain is it going to give you? Well, I'll show you some examples. It's a factor of 2, maybe. We're not talking big gains in performance, not compared to data movements. So don't worry about that. I mean, in CUDA programming, shared memory is everything. Everyone talks about shared memory. But what they should really talk about is data movements, because that's what really slows you down. And when you've got a big application, tuning the kernels is kind of, you leave that for a while, because you've got a lot of thinking about data movements to do first of all. Yes?
Say you have explicitly vectorized your CPU code with some file intrinsics, SSE instructions.
Yes.
Can OpenACC accomplish that?
No, almost certainly not. It won't translate it. But if you've gone down the road of using SSE intrinsics, I would hope that you also have a more generic source version that is more, if you like, is more portable, and I would start with that for the OpenACC work, because it won't translate those intrinsics. So, a lot of kind of theory in this last lecture. Let's see it in action. So we've seen the Himeno code this morning. It's this finite difference code. It had these 4 loop nests. 2 were initialization and 2 were in the Jacobi compute routine. Which kernel should we tune? Well, the stencil. The other one is a really trivial loop nest, and we would hope it takes almost no time, and it does take almost no time. There's no point tuning that kernel. It doesn't affect your runtime. So, you know, the other kernels were ported to avoid too much data transfer, not because they needed GPU performance levels. So the first thing you can do is to choose the number of threads per thread block. It's one of the easiest choices. So you use the vector length clause. So you probably have a lot of kernels, not in Himeno, there's only one, but in a real code. You've got a lot of kernels, and you kind of think, well, it's probably worth looking at whether threads per block is a good tuning on all of these. Because you have to edit the source to put in the vector length clause and do a recompile, and each kernel you need to see, does this kernel speed up? Does that kernel get slower? Because the optimal number will probably be different for every kernel. There can be a fair amount of work in doing that. So what's a good way to do it? A good way to do it is put the vector length clause in, but put a CPP macro in there, and set that macro on the compile line. Then you don't have to edit the file to change this value. Do it right at the start, and then it's there for later, while you remember. And initially, put the same macro in for every kernel. Compile the code, run the code with profiling, and then look at the times for each kernel in that one profile. Then change this value and do it again, and then you're tuning all of your kernels at the same time. And then you say, kernel 1, I've got the profile data with all these different thread blocks. 256 is best. The other kernel, 128 was best. So you can tune them all by using the profiler. It lets you look at each kernel separately and do them all as one big tuning run, set of tuning runs. And then you can go in and hand tune these values. But remember, this tuning value will probably depend on the problem size. So make sure you tune the right problem. And if you run different problem sizes, you are going to have to tweak these values for different problem sizes. And different problem sizes could mean I've got a parallel code and I'm strong scaling, so the local problem size is changing as I vary the number of ranks. And in which case, you're going to have to tune each one separately if that's important. So it's just the way it works. So with this Himeno code, I've looked at 4 different problem sizes. So I'm thinking here that that is a strong scaling parallel code. So as I'm changing the number of ranks, I'm changing the local problem size. That's not what I'm doing. I mean, it's a scalar code. But that's why I'm thinking about all the different problem sizes here. We'll work in double precision, just because that happens to be what I worked in. We've got different vector length choices. So what I've done here is I've looked at 4 different problem sizes, and I've looked at the performance of the code, which is essentially the performance of the stencil kernel, because all the other kernels take no time. And what's best, as you can see, as I vary the problem size, for very small problems, 64 threads per block is best. Then it's 128, then it's 256, then it's 512 as I increase the problem size. So it is problem size dependent. The default is 128. So what improvement can I get over the performance of 128? Well, with problem size 2, 128 was best, so I can't improve. With problem size 1, if I chose 64, I get 4% improvement. Not very much, probably not worth bothering with. For problem size 3, 256 is 1% better. But for problem size 4, I can gain 69% by increasing the number of threads per block. That's worth doing. What else could I do? I could try changing the loop schedule. So we've got this IJK loop stencil. What could I try doing? Maybe I could collapse the inner two loops. Remember to repeat the reduction clause. I could collapse all three loops. Or perhaps I could go in and say, make the middle loop a worker loop so that this one is vector and this one is gang automatically. Don't forget the reduction clause because it's a user-inserted loop directive. So here's three different scheduling choices. And really, I've got no way of knowing which is best. So you try them. So three different scheduling choices. The other thing I'm going to do is try the cache clause. So I'm going to do the default schedule, but in the middle, I'm going to say, please reuse some data. Now, if I want complete reuse, each thread does nearest neighbors in I and j and k, so best reuse would come from caching this range of data, I minus 1 to I plus 1, j minus 1 to j plus 1, k minus 1 to k plus 1. But I use more shared memory, I spend more time packing the cache. Perhaps it would be better to only use reuse in I and j. I'm allowed to do that. It won't give me wrong answers. It's just I get less reuse, but maybe I take less time to get the cache packed. Or I could only do cache reuse in the I direction and not worry about j and k. Which is best? No answer. It depends. Although I almost always find that caching on the inner loop only gives best performance. So that's the one I'm going to try here. I tried the other ones, they were slower. Much slower, actually. So I've got three different schedules here, and I'm also going to try the default schedule with the cache clause. So default scheduling, collapsing the inner two loops, collapsing all three loops, trying a worker clause on the middle loop, or doing some caching just on the I direction. The vector length, just leave it as a default. And what happens? So here's for each problem size, I've got my 5 different algorithms. Again, which is best depends on the problem size. So the blue is the default here. So how does it compare? Well, compared to the default, collapse 3 gives me a 55% performance increase for the smallest problem size. Here, using the cache clause gives me a 6% performance increase relative to the default. Again, for problem size 3, cache is best, and cache is best for problem size 4. And again, I get a 65% increase here by using the cache relative to the default algorithm. So again, playing around with these is giving me performance increases, but I'm doing it with directives. I'm not having to rewrite CUDA kernels. It's a great productivity win for OpenACC that it's so easy to change the scheduling. Whereas with CUDA, you've got to change all of your mapping of thread IDX and block IDX onto loop iterations. So we've done two things. One thing is we took the default algorithm and we changed the number of threads per block. Then we took the default number of threads per block and we changed the algorithm. Really, we want to optimize the full space, don't we? Which is the best algorithm and the best number of threads per block. Of course, you start to get a lot of different things to try. It starts to become very complicated. You probably want some sort of automatic auto-tuning framework to just get you through this parameter space to find the best combinations. Is it worth the effort? Well, you might double the speed of a kernel. Is that worth it to you? Is what you've got to ask. How much difference will that make to the runtime of my application compared to the time I'm going to spend finding these optimal choices? But if I do that, if I choose the best algorithm and the best vector length, and I compare that to the default, which is 128 threads with the default schedule, what can I get? For all the problem sizes, I get a performance increase. For problem size 2, I get the least, but I can gain 30%, 60%, 70% in performance by doing this. So performance tuning can be worth it, but don't forget that we got a 20 times speed up by minimizing data movements. So do that first before you look at kernel optimizations. What are the general conclusions? More threads per block is better for larger local problem sizes. Collapse worked best for the small problems. Cache worked best for the large problems. And cache worked best just in the I direction. But your mileage may vary, as they say. Different applications, the balance will be different. So if you want to do tuning, do that. Look at your application, but don't do it until you've reached that point. So what do you want to do? We're scheduled for a break now. I can do one more bit and we can have the break, or you can have the break now. Who votes for break now? Who votes for talk now? Are you saying that some of the things I say are not interesting? I'm going to talk about asynchronicity. So it's, does that change your vote? Yes. 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 The idea is that the compiler is targeting the OpenACC for a particular architecture. So in this case, it's for the NVIDIA Kepler GPU, which is why we loaded that Cray Accel NVIDIA 35 module, which you might not guess from the name is telling it that it's a Kepler K20. But, so it does know that. The compiler knows how much shared memory there is, and it won't let you cache more data than there is in shared memory. But it will let you use the shared memory, and in doing so, you may make the performance worse because internally it was going to use that shared memory for something else. So it may decide not to honor your cache clause. It may decide to honor it, but it may not be optimal performance, which is why you should try it rather than just always use it. It shouldn't lead to incorrect results in doing it, but it may lead to not optimal performance. Yes. I mean, the more shared memory you use, it starts to affect things like occupancy. It affects things like occupancy, how many thread blocks it can schedule at the same time. So, this is another reason why it can affect performance. So you need to use it as an experiment, and use it as an experiment once you've got everything working correctly and you've got the data movements cut down. Well, there didn't seem to be a clear preference, so I'll do another bit of talking then. So howl now if that's not what you would. So you've done all of this. You've tuned it. You've got the data movements sorted out. You've got it vectorizing properly. You've even done some tuning of the schedules. What more can you do? So what you would like to be able to do now is to go a little bit beyond this and use the asynchronous features of OpenACC. Again, if you've done CUDA and you've used streams, it's exactly the same technology, just with a different name. If you've not, then this is what I'm going to talk about. So when the CPU has a kernel, it sends it to the GPU to be executed, but immediately control goes back to the CPU and it can go and do something else. So if you want to get the results from that computation, then either the CPU must wait until it must wait until the GPU is finished. So you can either explicitly say, wait until it's finished, or you might test and say, has it finished? And if not, well, I've got something else I could just go off and do, and then I'll come back and test again in a minute. Is it okay? Should I break now? Or? No. I just wondered if you were saying that we must have a break now because the coffee machine will be turned off or something. Ah, right. So the hardware is supporting this asynchronicity. But generally, when you first start off, you don't really use it. And the compiler will use some of it automatically. And it will do it automatically, but it's probably be conservative. It will probably wait for things to finish because you need the data for the next step. It may be smarter, and it may spot that actually I could get that going and that going, and the result would still be correct. So the compiler does do some of this automatically using the asynchronicity. To control how much it's done, there's this ACC model flag where you can say, don't do any asynchronicity, wait for everything to complete each time it's done. And that's what we did to get the profiles, which showed the kernel time. You can get some overlap of computational kernels. This is the default. Or you can be more aggressive and set it to be all, and that's a performance tuning option that you can try with your code without any code change. So you can change. This is a Cray specific thing. But it's probably the case that if there is a way to exploit asynchronicity in your code, you probably need to do it yourself with user control. So there is this thing called the async clause that you can put onto the parallel or the kernels or the update. And instead of waiting for this operation to finish, it will happen in the background. And you are then in charge of waiting for the result to be ready before you use it, for that kernel to finish or for the data transfer to finish. If you don't wait, you will get the wrong answer. There's no protection when you start using this. It's all up to you. And one thing you do have to be aware of is when you get to the end of a subprogram, a routine, and you return, there's no automatic waiting there. You still don't know that these GPU kernels are finished. So you put in these synchronization points, you put in these wait directives, and then in between, things that have been launched with this async clause may overlap. You could get overlap of computational kernels. You might get overlap of computation and data transfers. Data transfers in the same direction on the PCI bus won't overlap, but the runtime will automatically serialize them. So you can't get a mistake because the hardware didn't support this asynchronicity. It won't say, you asked me to do it, I don't know how to do it, so I'll just trash all your answers. But if the hardware does support it, it will do what you say. Even if these operations are serializing, if you say copy A across, copy B across, then copy C across in separate directives, making them asynchronous is a good idea, even if they're serializing, because they're queued ready. As soon as the bus is free, the next one goes through. So it can be a good thing to do, even if there is some serialization because of the hardware. So that's one thing. That's where you say, I think these things can overlap. But quite often you want more control than that. And this is where you use the async clause, but with a handle, with a label. And what you say is that you can launch tasks if they're launched with an async clause and the same value of this handle, they will execute asynchronously, but you know that they will execute in order on the GPU. So the second one won't execute until the first one is finished. And when the second one is finished, the third one will start. They won't get out of order. They may not be immediate. There may be a delay between number 1 finishing and number 2 starting, but they will be in order. So if you've got a sequence of things to be done to an array, launching them as this stream of tasks, so async, all with the same label for each of these kernels and maybe data transfers, is a good thing to do. And you can then wait at the end to make sure this stream of tasks has finished. One handle. So you say you've got 3 kernels that are going to process the same array, one after the other. So you say parallel loop async 1, parallel loop async 1, parallel loop async 1. The host will just launch these and be back ready to do something else almost immediately. And then you'll have 3 tasks queued in the GPU, and the second one won't execute until the first one is finished. They block each other. So that's one thing you can do. But let's say you've got, 2 different things to do. You've got one array to process with 3 things to do to it, another array to process with 3 things to do with it, but they're independent, these 2 arrays. You can have a stream of tasks that's processing the first array and a stream of tasks that's processing the second array. There's no reason why these streams don't overlap, because they can't conflict, because they're doing different things, independent. In that case, what you can do is you launch a set of kernels with 1 handle value to process the first array. You launch a set of kernels to process the second array with a different handle value. Because these labels are different, the GPU runtime is free to overlap these tasks as it sees fit. You don't have any control of how it does the overlap. Stream 1 and stream 2 could be mixed in any combinations. Tasks within stream 1 will remain in order. Tasks within stream 2 will remain in order. But how tasks from different streams get scheduled on the GPU, it's up to the runtime. You don't have to worry about it. There's nothing you can do, so don't worry about it. And then you can wait. You can wait for a particular stream of tasks to finish, or you can wait for all the streams to complete. So here's a really simple example. I've got an array, and this array is basically a set of chunks, and I'm going to process it 1 chunk at a time. And when I process a chunk of my array, it's completely independent to every other chunk. So I can process 1 chunk of the array and another chunk of the array, and these are completely independent. There's no conflict between here. It's a simple sort of pipelining task, processing frames of a movie. You process 1 frame, you process another frame, there's no interaction. You can do these, they're naively parallel. So what does my workflow look like? Well, each processing this means my data's on the CPU. I'm going to need to take a piece of the data to the GPU, process it with a kernel, and then bring it back. And obviously, these tasks must be in order, but I do this for every slice of the array, every chunk, and each chunk is independent. So this sequence of operations, this stream, could overlap with the processing of other chunks. So what would I do? I would say, well, put some space on the GPU because I'm going to need to put these arrays there, but don't move any data yet. And then at the bottom, end the data region. Here's my loop over the independent chunks. It's a sequential loop. It's not a parallelized loop. So for each chunk, what's going to happen? First of all, copy across all the data associated with that chunk. Then process that chunk, so fix j, then copy the result back for fix j, then go round and do the next chunk. These tasks, the data copy, the process, the data copy, must be sequential, so I give them the same handle, the same value inside here, which is j. Why not? Because the idea is different slices are processed independently. They should be in different streams of tasks. Each slice is labeled by j, so that's the perfect handle to use, so that each stream has a different handle. So in principle, what's going to happen is that it's going to start this for the first chunk. It's going to start moving the data. The second chunk is queued up, but it can't do anything yet because the PCI bus is busy. But as soon as the first chunk is there, the second chunk will start moving. While the second chunk is moving, the first chunk is being processed. Then, while the first chunk comes back to the CPU, the second is being processed, and the third is moving to the GPU. So I get this threefold overlap going on here, because there's three operations here, essentially. So if I look at a timeline view, time going across here, each one of these lines is a stream. Within this stream, what do you see? A data transfer, a kernel operation, a data transfer. If I just run the code on CPU, it took 3 seconds. If I run it on GPU, it took, basically, it sped up. If I then used the asynchronicity to overlap these, I got roughly a factor of 3 performance gain here, because I chose it that it was very balanced in terms of data transfer and kernel compute time. So I'm getting data transfer here to the GPU, overlapping with a kernel communication, overlapping with a data transfer from the GPU, all at the same time, but in different streams. So I've got streams going up there. How many streams are there? Well, in fact, there's only 16. That's what the hardware allows you to have. This is a Fermi GPU. So what happens when I get to number 17? When j is 17 in this loop nest? Well, don't worry about it. The compiler takes care of it. It just does a mod, and it puts it back in the first one. So here, later on, if this is iteration, if this is slice 1, then 2, then 3, then 4, then 5, then 6, then 7, and 8, 9, 10, 11, 12, 13, 14, 15, and numbers, what did I start at? 1. And 16 is up there. Number 17 is back here in the first stream. So it takes care of that for you. If you've got a pipelining type thing, independent operations, this sort of approach works really well. If you've got a code where you actually have, it's more complicated, like the Himeno code, where you're processing, you're not processing independent, your computational tasks are not independent, one depends upon another. It's harder to get this overlap because you're looking for tasks that you can overlap one with the other. And you don't find so many tasks. In the Himeno code, there's no tasks to overlap. I can't copy work 2 back into P until I've done the stencil from P to work 2. There's no way to overlap those tasks because they depend upon each other. So OpenACC 1 had some async in it. What came new in OpenACC 2 was it got more complicated. In OpenACC 1, what you could say is, when you've done this, do this, and when you've done this, do this, and when you've done this, do this, and it's a linear stream of one operation after another. What you couldn't say was, when you've done this, do this and this, but they can be in parallel. Or, when this has finished and that has finished, which may be executing in parallel, then I would like you to do this. If you wanted to do that, you had to have explicit host synchronization. You had to put a wait directive in to say that had finished. So you could have linear streams of tasks, but you couldn't have a dependency tree where multiple things depended on one thing or one thing depended on multiple things. OpenACC changed this. So here, do A and B, at the same time, but B must follow A. At the same time, you could be doing C. When A and B have finished and C have finished, then you can do D. When D is finished, you can do E, but you can also do F and G in parallel, but G must follow F. It's a bit abstract, I know, but it's sort of, it's not just a single stream of operations. There's a tree to it. There's depending on more than one thing. And the way this works in OpenACC now is that you say, do A, do B, same handle, so B will follow A. Do C with a different handle, so it can overlap. The two streams can overlap. But then here I say, here's D. When you do this kernel, wait for this stream and this stream to finish. And then you can start and use this stream. And then down here I say, when D is finished, so wait on this, then you can do E in this stream. And also when D is finished, you can do F and then G. And G will follow F because they've got the same handle in there. So it's this concept of what they call the asynchronous wait. The point here is that when I run this on the CPU, I get to this point almost immediately. There's no waiting by the CPU in order to launch this kernel. It doesn't have to wait for this and wait for that. The CPU has offloaded all of these tasks, and all the dependencies are taken care on the GPU. And this is really good, because if you've got something else the CPU could be doing, you've got much more time for it to go off and do that. And then you can wait to know these have all finished. So that's where this asynchronicity comes in. But to use this, you need to know your code. You need to know what tasks there are. You need to know which tasks are independent, which tasks are depend on what. You need to know the dependency tree. Yes, sorry.
All these trees must somehow share.
Yes, they do. So the amount of overlap that you get will depend on the GPU runtime will decide. It might decide that there's actually no overlap at all. It will respect the sequence, but it doesn't actually get any overlap going on. But that's a hardware thing. The programming models, you can put this dependency tree in. It might decide to do A, then B, then C, then D, then E, then F, then G. And that would respect that dependency tree. But it hasn't taken advantage of any potential overlap between these streams here. I think the way the scheduler works, the GPU queues, I think the memory isn't. The memory is either allocated anyway because of your data region, or the memory is allocated at the start of the parallel region. I think the scheduler will take care of that, but maybe that's a question for Peter Messmer from NVIDIA tomorrow. The details of that. The idea should be that the compiler will take care of that for you, and you don't need to know that. If you want to take advantage of this, you need to know your code, so you know what it does and where, what the dependency tree is. You need to know the algorithm, because you might need to change the code to make the task-based parallelism more obvious. And you might need to know the science to say, well, actually, there's a different algorithm I could do to do the same science that has better task-based overlap. This is what I say, OpenACC is great for productivity, implementing all of this, but it doesn't do the thinking. That's where you come in. So that was all I was going to say. I've got an actual example later of using this. But again, don't use the asynchronicity until you've got a working code, you've got the data movements sorted out. You know, because otherwise you're just wasting your time. Yes? There? That's actually needed. Well, it's a good question. It's a good question. I'm just thinking, you know, what does it mean to end a data region if there's still processing of the data going on? I think what it means is wrong answers. I think it is up to you not to end the data region without doing the right synchronization. Otherwise, it's a programming error, not a compiler error.
So if I want the CPU to do something else in between, how would I do that?
Well, within a data region, I mean, you are free, for instance, there to put CPU code. You're free to put CPU code there if you want. I mean, the parallel bit is in here. This is the parallel loop. This is a serial piece of code. This is a directive within serial code. I can do anything I like before I do the wait. But I mustn't end the data region until I know that the GPU compute is finished. That definitely here, because when I end the data region, these arrays are going to be deleted out of the GPU memory. If this was a present, because this was a nested data region, I might get away with it, because actually the data stays in the GPU. The data region would then be a sort of, just a way of saying the data is already on the GPU. So I might get away with it then. But you need to be careful. That's why I say get a code that's working and you've got all the checksums to make sure it's working before you start putting the asynchronicity in. And not all codes can benefit from it. I mean, there's some codes that just are so... We'll look at the multi-grid example a bit later. And there's just, I looked at the code, there's nowhere to use it. Every task depends on the one before. So there's no place to get any sort of task-based overlap. And you can see this just by following how the arrays move through the call tree. So should we break for coffee? Are there any more questions? Well, if there are, you can always ask me during the coffee break. There's n elements starting at 0. If you use one language or the other, it's easy, you just remember. If you're trying to do examples in both of them, you end up making mistakes because you forget. The runtime commentary, that Cray-ACC debug, is brilliant for finding these errors because it tells you the name of the array and it tells you how many bytes. So you look at the number of bytes, you divide by 4 to tell you the number of floats, and you immediately see, I've done one too few. That's why I'm getting the wrong answer, because the last array element didn't move because I mixed up these syntaxes. If you do slices on multi-dimensional arrays, it has to be a contiguous block of data. What that means is that if you're doing Fortran, you have to have all of the elements in the left ones, and then an incomplete slice has to be on the right. And you can only have one incomplete slice. And then that's one block of memory. For C, it's the same, except it's the other way around. So for C, the fastest moving indices, which are on the right, have to be complete slices, and then the incomplete one is only one of them at the left-hand side, because it has to be one block of memory. If you need to send a number of slices, you'll need to have a number of separate directives. If you're doing C especially, you'll often see, you'll do some OpenACC and you'll see errors from the compiler, unshaped pointer, which is a really useful error message because it tells you nothing. What it's telling you is that I didn't know how much data to move. And that's because in C and C++, arrays are just pointers, generally. They point to the start of the block of memory. So if you say copy C, where C is an array, what you're really saying is C is a memory address. How much data should it move? It doesn't know. So in C and C++, if you're using dynamically allocated arrays or arrays passed by reference, you will often need to specify the data movements explicitly, and you will need to specify the slice, even if it's the whole array, just because the compiler's got no other way of knowing how much data you plan to move. In Fortran, it's different, because in Fortran, an array is not just a pointer. It's actually this array descriptor, which contains all sorts of information about the shape of the array and the size of the array. And so the compiler can hook into that information to work this out for itself. But in C, you often have to be explicit. So if you hit these errors, that's what you need, the halos of that array. And again, this update clause allows you to do that. So with a data region, there's synchronization points at the start and the end, automatically, because you've said copy in or you've said copy out. But within it, there's no synchronization. And the way you add this synchronization is you use the update directive. So, and this is a manual copy. This isn't something the compiler does automatically for you. It's you saying, I need to get these values back to the CPU now, or I need to send updated values to the GPU now. And these are directives, and the directives are whatever, hash, pragma, ACC, and then update host A, B. And what this will mean is that the arrays A and B, which are on the device, the GPU, these will be copied to the host, which is the CPU. So host is telling you where they're ending up there. And if you do want to copy them from CPU to GPU, you say update device A, B. I mean, it could be, it's just a comma-separated list of arrays. In OpenACC 2, instead of using the word host, you can use the word self. This is supposed to make things clearer when you have self-hosted accelerators. But when you start to think, what does a self-hosted accelerator mean? I don't think it makes anything more clear, but you'll sometimes see self instead of host for this keyword. So you put these directives in the code yourself at the point where you want this data to move. And by default, it's a synchronous operation. The CPU will wait while that data is moved. Now, you may want to get the data moving and do something else whilst it's moving, and we'll cover later on how you do that. But if you don't tell it to do it in the background, it waits for this operation to complete. If you only want to move part of an array, then you want to use a syntax, an array section syntax, a slicing syntax to only move some of the data. If you use Fortran, well, it's just the same as you'd do. You'd say to send the first n elements of the array, you'd say update, and then you'd say a brackets 1 colon n. And that would be element 1 to element n. If you're using C or C++, it looks the same, but it's different. So here, this doesn't transfer elements 0 to elements n. That would be n plus 1 elements. It transfers a bit more about the scheduling. One of the things, I mean, the way the Cray compiler works when it compiles OpenACC is the Cray compiler has its optimizer in it. And if it also has something that generates PTX. And PTX is like assembly code for GPUs. It's not quite the very lowest level, but it's the lowest level that you'll ever see if you're not working for an NVIDIA. So the compiler generates this PTX directly in the same way that NVIDIA, the NVCC compiler, takes CUDA and generates PTX. So CUDA and OpenACC run on the GPU in a very similar fashion. And this is why the interoperability works well. But what the Cray compiler doesn't do, I mean, some people say, oh, could I see an intermediate CUDA that's where the Cray compiler, you know, the compiler generates a CUDA and the CUDA is then compiled to the PTX? And the answer is no, because it doesn't exist. The PGI compiler does have an intermediate CUDA, but it's unreadable. I mean, where you can read it, but there's no loops. There's just, jump non-zero type statements. It's very low level and not that useful. So the reason Cray doesn't do an intermediate CUDA, other than it would impact performance, is that that would be a source-to-source translation, and it's very hard to preserve debugging symbols when you do that. So when you use the debugger, you're taking advantage of the fact that it's going straight from your Fortran or C to PTX with the right dwarf information, that the debugger knows the right variable names. And so the decision was taken that using tools like a debugger is far more useful to users than having an intermediate CUDA to look at. So in this talk, I'm going to go through a few directives that I haven't talked about before, a little bit about the difference between parallel and kernels, and a little bit of lessons I've learned along the way when I've been using it. Minimizing data movements is something that you want to do, and we had this idea of data regions. So you should keep the data on the GPU as long as possible with big data regions that span as much of your code as you can. Only move data when you need to. So within that data region, if you need to move some data back to the CPU, you don't want to synchronize everything by ending the data region. You can use a directive called update to just move the amount of data that you want to move. And when you move the data, only move what you need. If you don't need the whole array, don't move the whole array. If all you're trying to do is move the edges of the array, the halo, because you're going to do MPI to send them to the nearest neighbor processes, don't move the whole array, just move to do.
Sorry. So that means that it is something that is defined at the compile time in the pragma now. So n must be known at the compile time.
No, n can be known at runtime. It's fine for n to be a runtime thing here. It's in the pragma and it's compiled, but all of these things get turned into API calls, calls to runtime libraries. And these can be passed arguments. So this n doesn't have to be fixed at compile time. It can be determined at runtime, which if you're using dynamically allocated arrays, of course, is what you want. Yeah, that's fine.
So you don't specify something like size of double or whatever? You give them a number?
No, you give the units in array elements. And it,
Clever enough to-
yes, it knows that it works out what type it is to get that right. Yeah, so you work in elements, not in bytes. So sometimes you need to put more data clauses in than you thought you'd have to. And if this was a present clause, you might have to say present C and a shaping argument there. This is what we've been talking about before. This was to do with present, that if you want to share data between kernels, then instead of saying copy, copy in, copy out, create, you just use present. And then it has to be there on the GPU. And it will use the version that's on the GPU. And it will check whether it's there. If it's not there, you get a runtime error. And it does this because the compiler and the runtime maintain a table that know which CPU memory addresses have been mapped onto the GPU and where they are in the GPU memory. And so it checks this table to see whether it exists there or not. If you sometimes call a routine from inside a data region and the data is present, but at other times in the same code, you call the same routine from outside a data region and you want the data to be processed on the GPU, but it's not on the GPU, so it should first move there. What you say is, instead of using the present clause for these kernels, or this in the data region, you say present or copy in, present or copy out, present or create. And this will it'll first check, is it present? If not, it will follow it'll either do copy or copy in or copy out or create, just like we were doing before. So the data will always be processed on the GPU. It's just whether or not it needed to be moved to the GPU first in order to do that processing. as I say, for a lot of real codes, where you know that the call tree is such that all calls to this routine are within this data region, and you know the data must therefore always be present unless something disastrous has happened, it's better to use present because you'll get a runtime error rather than get just a wrong answer when your code runs to completion. The other thing you might say is that I'm going to call a routine. Sometimes I'm going to call it from a data region, from inside a data region. Yeah, sometimes I'm going to call a routine from inside a data region. Then the data is this is a bit confusing. I'll change this around. Sometimes I'm going to call this routine, and the data is on the host, and I'd like to process the data on the host. Sometimes I'm going to call it, and the data is present on the GPU, and I want to process it on the GPU. How do I decide what to do there? Well, there's an if clause. An if clause can be applied to the parallel kernels. I think the data as well, data regions, and you can decide at runtime whether to execute your loop nest on the CPU or on the accelerator. It executes on the GPU if it's true, otherwise on the CPU. So that's good, but the argument here is what goes inside that if clause. If what? I mean, one way we could do it is we pass a logical in. So we pass in data that we know is on the CPU, and we pass in a logical variable that says true, well, so false. And we know, or we pass in data that we know is on the GPU, and we pass in a logical that's true, and then we just put that logical in the if clause. Would be one way to do it, but we'd have to put this extra logical in there, and you're changing your code to do this. There is a way, there is a runtime library call that you can do to check whether data is on the CPU or the GPU. So you could use that runtime call if this is really something that you'd want to do.